Hey everyone, welcome to another episode of Robo Papers. Super glad to have with us today Xue Su. Actually, we're quite ambitious today. We'll try to cover two papers from Xue Su's lab. So one of it is called VERTIFORMER, a data-efficient multitask transformer for off-road robot mobility. And then another paper which I think is super crazy. It's called DOM Cars Don't Fly or Do They? In-Air Vehicle Maneuver for High-Speed Off-Road Navigation. Now, I mean, they all sound mouthful, but I think once Xue Su starts sharing the video, it's pretty compelling. So anyway, great to have you, Xue Su.
Hi everyone. So my name is Xue Su Xiao. So I'm an assistant professor in computer science department at George Mason University. So I'm a roboticist. So I don't know if you can see the banner in the background. So I'm a field roboticist. I work on robots that work in the field, right? Work in the field meaning outdoors. Indoors also count as field, but I want robots to work in the real world to be in service of the real human users of robots. So we work specifically on motion planning to plan the motion to build very capable and locomotors, in land, at sea, and also in air, right? We also use machine learning techniques to make those motion planners more intelligent, including like working with, in-learning expert users, working with learning from its own experiences or learning from other robots' experiences to improve the motion planning performances. Eventually, the goal is to put robots in the field, right? Everything is in service of making field robotics more robustly deployable so they can be helpful for us. That's a very quick high-level view of the research we have been doing in the robotics lab at George Mason University.
That's awesome. Maybe you can start sharing screen and you can quickly give two overviews of both the papers, and then we can dive into one and then the next one.
Let's see. Okay. I guess maybe first of all, let me give a quick overview of like two research directions we have been doing in our lab. So we work on this direction called off-road mobility a lot. Especially we call it extreme off-road mobility. So those are the two directions we have been pursued, somewhat orthogonal, but also very related. So one is on the left, we call it high-speed navigation, right? So high-speed off-road navigation. You want to drive a robot in off-road terrain. You don't know anything about the terrain in advance, but you want to drive over them as quickly as you can. So we like to say driving at the edge of at the limit of the robot, right? So you want it to drive fast, but you also want to maintain high accuracy. You don't want to sliding all over the places. You don't want to collide with the wall, or you don't want to fall off a cliff. How can you maintain accuracy while also drive as quickly as possible? So this is the high speed, off-road terrain. On the right-hand side, you see another direction, somewhat orthogonal. This is not about driving fast. This is about, we call it driving over vertically challenging terrain. So as you can see in this video here, if you don't plan your motion precisely enough, you may roll over the vehicle when you are trying to crawl over those large rocks. Those rocks are sometimes even bigger than the vehicles themselves. Usually they will be treated as obstacles. But here, we want the robot to drive over them and also with very limited mechanical capability. So all these are just wheeled robots. Could be 4-wheeled, 6-wheeled. We actually have a fleet of robots with somewhat limited mechanical capabilities. So they don't have legs. They are not a lagged wheel, for example. Just passive suspension, just all-wheel drive, just differential locks. That's all the minimum requirements we have on the mechanical side. How can you make them driving over very, very challenging terrain without rolling over, as you have seen in the video, and without getting stuck between rocks? How can you smoothly navigate to the goal as quickly as possible? So that's what we are working on. So I'm not going to talk about this high speed and on the left-hand side yet. So we do have a lot of work in this, but I'm not going to do this. But the first work, we are going to cover today is called VERTIFORMER, which is doing, this vertical challenging terrain using a transformer model. And we do it in a multitask setup in terms of inverse kinodynamics, forward kinodynamics, learning and navigation policy, or we can also reconstruct a terrain patch underneath the vehicle as well, right? So another paper Michael mentioned, this crazy flying car project, is actually a combination of both of these. So I like to ask this question. So what if you combine these two directions together? What if you want to drive a vehicle at high speed, but also across vertically challenging terrain? It's very, very rugged terrain, right? So this brings us to our, DOM planner paper, which I can actually, Michael, should I play a video to show how it looks like?
Yeah, I think maybe what we can do is you can start with one paper and then it could be either you can start with DOM first and then
right. So it's called in-air maneuver. So when you drive at high speed on rugged terrain, on uneven terrain, it's inevitable sometimes your vehicle may be in air, right? This is, of course, the extreme case. We built a ramp so we can launch it, right? What we want to do is we want to control the altitude in air with limited controls, throttle and steering. For example, here, that is the most impressive video, I think, across this whole 4 minutes video. As you can see here, the vehicle is launching off the ramp with an almost 90-degree roll angle, right? But if you land with this, you will damage the vehicle for sure, because you don't want your side wheels to touch the ground, and then who knows what will happen, right? So we are controlling the altitude in air by only using the throttle command and also the steering command. That's what you are seeing here. As you can see, it's trying to correct it and to land on the grass almost flat, right? So here, it's just a bunch of different, examples we show we can launch it in air, and in most of the cases, the vehicle will be able to land almost flat on the ground. And of course, to do this kind of experiment is very, very dangerous because we damage lots of our robots, right? Because you fly in them in air, if you don't control it precisely, bad things will happen. They did happen a lot, right? So that's why we built this indoor turntable/gimbal system, so we can study, the dynamics control in the air in a safer manner, right? Here you can see, so again, a reminder, there's nothing we modified this robot. We didn't modify anything. So it's just like your race car with throttle command, brake, right? So that's the same thing, linear velocity, and also steering, right? So or you can call it angular velocity, the steering of the front wheels. That's the only controls we have over the vehicle. We didn't add any counterweight. We didn't add any propellers or anything to this vehicle. Everything is just a regular car. And then as you can see here, you can actually achieve a lot of different, pose in the air, right? So here, the red and the black is basically we compare against our baselines. So green is our DOM planner. We call it DOM because it is named after Dominic Toretto, who makes car fly. So does our planner. So we call it DOM planner. And this fly is physics-informed and learning-based dynamics. I actually forgot the whole acronym, but PHLI pronounces as fly because we make cars fly, right? So fly is the model. It is a hybrid model based on some learning and also some classical basic integration, physics-based principles, and then we combine this hybrid model with a newly developed sampling-based motion planner, which has some very interesting features, which I will go into details later, right? So we compare this DOM plus fly, which is showing green here, on a few tasks. For example, here you see it's trajectory tracking, right? So we wanted to reach a few poses in the air using our planner, DOM planner, and the fly model. You can also do the same thing with a simple PID controller, right? So you basically, based on the error, you control your PID gains trying to reach that. But there's a problem with that because, for example, PID is not fast enough. PID may reach the acceleration limit, may not be able to keep going, right? There's also this problem of, do you want to keep going on one side rather than going all the way around? Because that's what the planner can do, but not a PID controller, right? This is a time goal region. That is a very important task when we are maneuvering actually in air, because when we launch, we roughly know how we will have in air time. And when we want to land, we want to hit that pose precisely at that point, right? With this, I'm gonna stop this video and also mute myself to play the video. So here you actually see, right here, you actually see one of the wheels come off. Yep, right here, right? So
Well,
we did break lots of robots during our experiments. We have multiple robots in the lab just for spare parts when doing the experiments.
Well, firstly, incredible. I love it when folks try to evaluate whatever they're building in the real world. We have seen too many demos that just work. So in your case, clearly, if it doesn't work, things break, right? Yeah, I got so many questions, man. Yeah, Chris, if you don't mind, I'll just start asking some. So you were saying that this is a physics-based as well as using a bit of like machine learning. Could you go through a little bit like how that part works? I think you call it fly, right? PH.
Yes. Of course, let me stop sharing and share my screen again. Let me go to this paper here. So it's called DOM, Cars Don't Fly, or Do They? So eventually, it is a little bit counterintuitive when we say, you can control the vehicle pose in air because you don't have a propeller like a drone, right? So what we find out is if you have a big enough wheel, the inertia effect plus the gyroscopic effect of the front wheels will give you some freedom for you to control the pitch and roll angle. Not yaw though. You won't be able to control the yaw. We actually have
this way, right?
Yaw is this way, like, yes. Or pitch is going up and down like this, and the roll is like this, right? So if you use the aerospace terminology, right? Roll, pitch, yaw. You do have control over the roll. You can roll the vehicle, you can pitch the vehicle, but you cannot yaw the vehicle, right? So
Interesting.
we actually in this whole we call it fly. Fly is actually for physics and learning based model for in-air vehicle maneuver. Fly, PHLI. So in this paper, we actually use a learning approach to learn structural dynamics because it's very difficult for us to model every single quantity in there. For example, we need to know, the angular momentum of the vehicle chassis and also of each wheels. Those are very difficult to model. But first of all, we actually, derive all the underlying physics, assuming if we have all these quantities, why this is possible, right? So what we are able to control is not just the roll angle or roll velocity, it's actually the roll and the pitch acceleration, second order derivatives here, right? So I guess this is a good, figure to illustrate everything, right? So we use a simple bicycle model. So it has 4 wheels here. You can assume that's a bicycle model with a front wheel, steerable, and rear wheel, which is not. That's the bicycle model we used, right? Each of the tires or wheels have some inertia. You also need to have a 4-wheel drive vehicle. If you have only a rear wheel drive vehicle, that won't work. You won't be able to control the roll, but you are still able to control the pitch, right? So the idea here is if you accelerate the rear wheel or the front wheel, because you need to gain some momentum on the wheel, right? There's an opposite effect which will be acting on your chassis. So that is the torque due to inertia effect. We can have it on our vehicle chassis. But for the rear wheel, there's very limited effect because you cannot steer it. So everything is along the vehicle direction. Then if you accelerate or you decelerate, this torque is only gonna cause a torque along the pitch axis, which is this. If you think about it, it's difficult for me to explain this on the screen. If you use your right-hand rule, right, the torque is always for spinning these 2 rear wheels, always going to be along this y-axis. So that's why you gather some momentum to pitch the vehicle going up and down. So that's for the rear wheel. The front wheel is a little bit more complex because it has a steering angle. You can steer left and steer right. Right? Well, because it's a 4-wheel drive, so it's also when you accelerate or when you decelerate, you still have some momentum being acted upon the vehicle chassis. Now you need to decompose it, right? You have this, this momentum here. You basically use your sine and cosine angle to decompose them. One along the x direction, the other along the y direction. Then the component on your y direction will affect your pitch, same as the rear wheel, right? Instead of all the inertia goes to affecting your pitch axis here, so only a portion of it along the y-axis will affect the pitch, right? That combined with the rear wheel, that will affect your pitch using inertia effect, only inertia effect, right? And also the same inertia effect because when you decompose, you will also have a component of the front wheel inertia along the x-axis. So if you, again, right-hand rule, right, you will have you will actually affect your roll angle here as well. So that's why if you decompose the front wheels, you will have a component on the y and another component on the x. So you can affect both roll and pitch. So for the inertia effect, basically to summarize the inertia effect, so rear wheels are only affecting the pitch, while the front wheels are affecting both the pitch and the roll based on the decomposed components. That is the inertia effect. That's one. And then the second effect is called the gyroscopic effect. So this is a little bit more complex compared to the inertia effect. So the idea of this inertia gyroscopic effect is whenever you have a spinning mass, right, you have some certain angular momentum here. When you are trying to apply a torque on this axis, so that's your spinning, you have basically this here, right? So if you apply a torque, try to push this torque axis, you will actually get another force, which is pushing your rotation axis to go along the torque. That is basically the gyroscopic effect. So it's a little bit difficult to explain using this paper. There's actually a very good tutorial online, I think it's from a MIT professor. If you go search for gyroscopic effect, you can find that. Very, very helpful, right? So I think the experiment is if you have a rope hanging a wheel, like a rope here, axis here, and you have a wheel spinning. If you spin the wheel fast enough, if you let go, the wheel won't come down. The wheel will actually rotate this way. That is the whole gyroscopic effect, because you have your gravity trying to push this down, so you have a torque going down, right? So that's the torque direction. And then your spinning axis is this way. It will try to chase this torque. So that is the gyroscopic effect. And this is also what we are trying to utilize here for the front wheel. So we have a spinning mass for the front wheel here. It is spinning. When we are trying to steer, right? So the spinning axis is this, right? So that's how you steer the front. That is how your front wheel steer. Also, sorry, not steer. Rotate. It's always rotating. Then when you try to steer the front wheel, you're trying to apply a torque to bend it, to turn it sideways, right? So that is saying a torque which is along this direction. Right hand rule here, right? So if you're trying to, so the torque trying to steer the wheels to turn to the side is basically along this way. Then it will cause, because of gyroscopic effect, right? It want to conserve its angular momentum of inertia here, which is here. And because you're applying a torque going up, that is why this axis will try to chase this. So you can imagine it's trying to flip the vehicle to start to roll here. So if you want it, also explain this more like mathematically. So this whole effect is called precession. And so basically the rotation axis is trying to chase the axis of the external torque. That whole effect is called precession here. Then the precession is actually also following the right hand rule. Right? This is the rotation axis. This is what it's trying to chase. It is trying to go there. And then based on the right-hand side rule, if you want to do this, your right hand is going this way. So the torque is actually going here. That is tau precession. That is the torque tau caused by this effect called precession, gyroscopic effect. Then we apply the same trick. This is the torque that is applying on the vehicle. Then you can decompose that into two components, one along X, one along Y here. Then that torque will also affect your roll and also your pitch. So eventually the roll and the pitch and how it's affecting it is to the second order derivative because that's a torque, right? You have your inertia, your mass of the vehicle. Then the torque is going to be applying on it. What you get is acceleration, right? So you have acceleration in terms of roll and acceleration in terms of pitch due to gyroscopic effect. Then if we combine the gyroscopic effect and the inertial effect as we described earlier, this is going to be the final thing. Right, I probably don't want to bore you guys with all the math, all the details, all the physics in here, but those are basically what I just described to give you the idea, right? So to summarize, inertial effect of both the front and the rear wheels. The rear wheels will have inertial effect to affecting the pitch acceleration. Front wheel will give you the inertial effect to affect the roll and the pitch acceleration. That's for inertial effect. For the gyroscopic effect, the rear wheel is out of the question because it cannot steer. So only the front wheel has gyroscopic effect. But that gyroscopic effect will give us a precession, a torque, tau precession, which can be decomposed and affecting both roll and pitch. So that is the idea here.
So then is the reason that you need the rear wheels is to like cancel out the pitch so you can level out the vehicle while also correcting the roll. Is that right? Is that right?
So front and rear wheel is not actually canceling each other. They are working together.
They're working together. Okay. Yeah.
So that is basically the physics behind it. So we have very detailed derivation of the physics or the math behind the scene. Everything is, I think, it's mathematically or physically right. However, the problem, as I mentioned earlier, is you need lots of quantities you have to estimate. For example, the inertia of the vehicle, the angular momentum of the vehicle along the roll, along the roll and pitch axis, and also you need the inertia of the wheel. One very, very difficult thing for you to estimate for the wheel is because we are driving very aggressively. The wheel is accelerating and decelerating very fast. Exactly. So that will also affect your whole inertia, right? That is why it's kind of difficult for us to, quantify all these like inertia of chassis along the roll axis, inertia of the chassis along the pitch axis. There's also quantities of, I think for the wheels, where are the wheels? All these, front wheel and rear wheel. All these things are very difficult for us to measure precisely. That is why we use machine learning to do that. But the good thing about deriving all these physics is we know how do we apply machine learning because we know our black box now. The black box is basically taking input our, of course, state and action. What is action? Action is the acceleration of the wheels and also the steering rate. All these are actions. And then the black box will give us our roll ... pitch ... You won't be able to control it. But yaw is also changing based on your initial conditions, right? Because if you have some yaw when you're trying to take off the vehicle, you have some yaw speed. Even though you cannot change the speed, the yaw speed is still going, and your yaw will be changing when the vehicle is in the air, right? So we also have yaw in here. So then we basically use a neural net, a very simple, very small neural net, to learn this G side here, parameterized by psi, mapping from our wheel acceleration and steering velocity into the second order derivative of the roll and pitch, right? And also you got yaw in there as well. All these are the other physics part, and it's nothing more than just double integration. You integrate over these, you will be able to derive your next roll and also your next RPM, and your steering angle and everything. So then you can put everything back together. You will have a full. We have an eight DOF model, 8-dimensional, and the dimensionality is actually here. This is our state. You have your roll dot, pitch dot, and yaw. So actually state is actually should be up here. So this is the goal, right? So we have the G here. So state is here. Roll dot, pitch dot, yaw dot, RPM, and psi t is the steering angle. So the action is RPM dot. So the first order, so how fast you want to accelerate or decelerate, and also how this is the velocity, the first order derivative of the steering angle. How fast you want to steer the front wheel. That's your action. That is your state. You will be able to learn that to learn the second order derivative using a neural net, and then use integration to integrate to get your next state. So this is our fly model.
Yeah. So I understand you use machine learning to basically learn that very difficult to estimate function. How do you collect the data? Is it collected in the real world or simulation?
Yes, it's all in real world. That's exactly the reason why we built this thing. All the data are collected on there. So we spend a lot of effort trying to make sure that the whole platform, the whole turntable is balanced well enough. So it is almost like the vehicle is floating in air, because we don't want the friction of the bearings and also some imbalanced load to affect that, right? So we try to very hard, try to make it very, very like the in-air condition. And then we basically apply all our actions to let the let the vehicle rotate on this turntable and collect data.
Yeah, at what kind of frequency are you collecting like each of these sensors, like the RPM? I mean, so, and let's say the IMU. I imagine this whole thing need to be is over in one second.
This
How
whole thing is
frequent
over
are
1
this?
second. Yeah, I don't remember the frequency on the top of my head, but I believe it's like maybe 20, 50 frequency. Not very fast, because the thing is, the whole thing is 1 or 2 seconds when the vehicle is in air, right?
Yeah, that's
But
right.
for this, you can put it forever. It's always suspended in air. You can collect as much data as you want. So I guess frequency is not a very important problem here, because we put it on there.
So you're only controlling it at like 50 hertz when you're deploying it too?
I think so. Not extremely high.
Interesting. Okay.
Yeah.
I guess that makes
Yeah.
sense.
Well, I imagine like your IMU better be very well calibrated.
Yeah.
How many
Right,
hours of data did you get? Sorry.
Actually, too much. Let me actually. So 1 hour of gimbal data. So,
Okay.
Yeah, not much, because the thing is the model is very small. I guess do they have any the neural net?
So, I think four layer. I saw it.
You saw
It's
that?
a four
layer
and perceptron.
Yeah, very, very simple thing.
Interesting.
Yeah.
So
that is the model, right? So I guess that's the interesting part of the model. But eventually, what we are doing is planning. We do motion planning, right? When it is in air, what you want to do to make sure it's land flat, using the model, right? So we use sampling-based motion planning, a very classical technique, right? You sample a lot of actions, trying to figure out what's the best, right? This whole DOM planner idea here is there's a lot of constraints, because for example, if the wheel is rotating at a higher speed, you won't be able to accelerate anymore, right? If you want to even reach the next goalpost, it's not possible for you to go this way. You may try to figure out to decelerate to go all the way around. So that's why a planner can help. If you use a PID controller, it won't. It will keep trying to accelerate, but you cannot. Right? So that's why the planner is very important here. All these are our limits whenever we are driving at the lower speed or driving at the higher speed. So you won't be able to just get unlimited acceleration on the wheels or for the steering. Another very important thing is a cost function we designed. So a very, very formal, a very, very classical cost function kind of format, right? You have some weight of each of the cost terms. So CI, you have a K terms. I is equal to I to K. Very simple cost function formulation. But what is special about this is here, this little t here. So this is saying the weight of each of your cost dimension is different in different time. So think about it. Why do we need this? So when we just launch a vehicle in the air, we don't really care if you get close to the goal on the velocity side of things. What we want is we want to quickly correct the pose, no derivative, just, your roll and your pitch and your angle to be as close as you want as possible. When you're getting closer to the ground, that's when you don't care about the pose anymore, because you probably have already get the pose roughly correct. What you care about is you want the roll dot, pitch dot, and the yaw dot correct, because you don't want impact. You don't want the vehicle is pitching very quickly, so you slam on the ground. So that's why we design it's a manually designed scheme to adjust, to regulate, to schedule the weight of each of those cost terms, so that it will focus on getting the orientation correct first. And then as you move closer and closer to the ground, you are trying to focus more on the velocity side. You're trying to make it as stable as possible. So when you land, you stably land without having a big pitch angle, pitch velocity, or big roll velocity. You want it to not only flat, which you have already achieved in the first few seconds, the first half a second. For the next half a second or the last second, you're trying to focus on make sure the velocity of the roll and the pitch and yaw are correct. And so that is what is special about this whole cost function for the DOM planner.
Cool. How do you know how long the flight's going to take? Does that
Yeah. Yes. It's a very good question. So there's no good way yet. This is going to be future work. So what we did is we built this whole ramp. We measure the height, how much we want, and also the angle. We basically have a target speed we want to launch a vehicle at, and then based on the speed, we can use projectile equation to compute how long it will last. I guess we tried very hard to make it as long as possible, because there's more flexibility for you to maneuver in air. I think that the maximum we get is like 2.5 seconds, no more than that. Because the thing is, the longer you have in air, the higher this will be, and the more dangerous it is when you land incorrectly. So I guess so for now we don't. We basically our student is driving the vehicle by hand, trying to aim at this ramp to launch it. Whenever it's on the ramp, there's a manual switch, say, hey, go take over. And then DOM and Fly will take over, try to maneuver this in air. It is a very good future work if we want to put this into a fully autonomous planner, right? So the vehicle will look at the ramp, estimate the angle of the ramp, and based on my current speed, I will know how long I will be in air, and then do auto planning. This is also going to be very interesting, because one thing to think about is it is also possible when you launch at a certain weird angle, it may not be possible for you to perfectly land flat. But what is the second best option, right? You know you won't be able to land flat, but what is the second best option for you to still avoid damaging the vehicle, right? So within the very small time window here.
That seems very useful. How many vehicles did you break testing this thing?
I was just gonna ask this. Gosh,
we broke a lot, I guess. So I guess we bought two vehicles, same vehicles. One is a robot, but the other we bought it just for spare parts, right?
Okay.
We basically replaced like wheels, wheel hub, the spoiler, the wing on the back. The wing on the back is actually the most commonly broken piece, because if you don't land correctly, whatever corner of this wing will touch the ground, you will stab the whole wing. There's so much. So we broke both wings multiple times. If you go to the lab, you will see like hot glue, all the super glues on the wings, like multiple places, because we broke lots of the wings. As you have seen in the video, the wheels also came off. So we also went back to the RC store, bought some like a reinforced, wheel hub, all these joints to reinforce it, so it won't break so easily.
yeah. This is so cool, man. But I actually have a few comments, but I suspect it's similar line of comments to your second paper. So if maybe if we can, do you have any more things you want to talk about this? Then if not, then we can try to swap to the other one.
Yeah. Well. Let me.
Yeah. Yep.
Probably, I can play a video here, or I can. So this is one direction. Let me full screen. So that's a problem we are trying to tackling. So we call it wheeled mobility on vertically challenging terrain. So the idea would be, how can you drive over these kind of terrain, avoiding rolling over like this, avoiding getting stuck. So it's a very good motion planning problem, and that motion planning problem is not in 2D space. It's not in SC2, not just X, Y, and yaw. It is also X, Y, Z, roll, pitch, and yaw, 6-dimensional. You basically, imagine the vehicle just as a drone, right? You control all the degrees of freedoms. So So for here, we are actually using a transformer model to model that. So here we took 3 different things, multimodality. So as you can see in this video, that is the terrain patch underneath the vehicle here. We are using this RGBD camera, which is a Microsoft Azure Connect, to build the elevation map. And then we crop the underlying elevation map. We call it the terrain patch here. On that patch, we also run VIO, visual inertial odometry. We will have the pulse of the vehicle. And also we know what is the throttle and the steering command we apply to the vehicle. So that's the action. So that is our multi-model input. We collect all these, then we feed all these into a transformer encoder. So all these are patches, action, patch, and history of those. And that is actually a special technique I can talk about, which is called unified representation. We feed that into the VERTI encoder, and then we can produce all these latent embeddings of the encoder. And because of VERTI encoder, we also have the decoder. For the decoder part, we are trying to predict the next 3 future pulses and actions, right? So we hook this up, encoder up with a decoder here using the context variable. We also flip a coin to randomly mask the action or the pulse. And we feed that in here, use cross attention, we put that into an encoder model. And the encoder model will reconstruct whatever is coming next, just as a regular full transformer model. One thing I want to mention here is this is not many work are doing this. There's some in robotics. So using a full transformer model, both encoder and decoder, right? So encoder, you can think from the NLP, terminology, it's more like the BERT kind of technologies, right? Based on mask modeling, trying to mask all these all these output tokens, try to predict that. Then you can learn for the sequence. So the decoder part is more like the GPT kind of thing, right? So you're trying to do next token prediction. But the original transformer paper, all you need is a attention paper from Google a couple years back. The most important transformer paper is actually doing both, right? It's not training the encoder alone. It is not training the decoder alone. It is training everything end to end. So that is what we are doing. So there's not many robotics papers are doing this because it needs a lot of data. And in principle, only doing encoder or only doing decoder is somewhat enough. But for our problem, it's actually very, very challenging. So we have application studies saying if we do only encoder and only decoder, it's not enough. So that is one. The other also very important thing here is we only need 1 hour of data. So I know, Michael, you probably want to ask where does the data come from? The data actually comes from this test bed in our lab. We have 3,000 pounds of rocks we put in the lab. So this is actually an older test bed. We actually expanded the whole test bed into a larger area. This is actually our ablation study. Unseen environment. So that's after we expand the whole environment, we also add foam. We add astroturf, which is also rugged, right? We also have those wooden planks. So that is our generalization text. So we collect 1 hour of data on this test bed here, only 1 hour. And we are able to train the entire VERTI encoder, VERTI decoder in an end-to-end manner. Okay, so there are 3 different techniques. Maybe it's better for me to switch the paper here, which I can explain a little bit more detail. 3 major contribution of this paper is, one is called, let me go down here. One is called unified state representation. Because as people know, right, robotics data is very scarce. We don't have lots of data. We are not doing CV, we're not doing NLP. We don't have the internet for us to scrape data from. So data is very scarce. So what we do here is we have this unified representation technique that is trying to map all these different modalities, including action. Image is basically the terrain patch underneath the vehicle, right? So it's a grayscale elevation map of the terrain patch, and also the pose. We're trying to use same function called FS to map them into the same, we call the unified space. That is saying we don't need to differentiate those multi-model input anymore because we don't have a lot of data. We shouldn't let the transformer figure out such, intra-model, relationships. Let's do it using our unified representation, right? And then what we did is after we map into it, we just concatenate those unified representation, throw them into into the transformer. So the only job of the transformer is trying to figure out the temporal relationship of all these modalities. It doesn't need to figure out all the intra-modality relationships, because that is taken care of by the unified representation. So compared to naive approach, like so existing work, most of them are just doing, each of those encoders are different for different modalities, and you try to concatenate the three different modalities together. So that is also okay if you have a lot of data. Then the transformer's job can be twofold. One is trying to figure out the intra-modality relationship between these three tokens here. And the second job is also trying to figure out the temporal relationship, because it's a transformer, it's a sequence of tokens in there, right? Here, using this, the transformer no longer need to worry about the intra-modality relationship anymore. That's taken care of by this. So it can only focus on the temporal relationship. So that's why it's very efficient. That is what allows us to only learn with 1 hour of data, right? So that's the very first contribution, the novelty of this paper. The second is actually the first unified state representation allow it to learn only with 1 hour of data, super data efficient. So the second, we call it the missing modality inferring technique, is actually what enables this multitask perspective of this transformer. So what we did is, in the decoder, when we feed in the action or pose, we actually randomly mask one of them. We can mask the pose here, only feeding the action. We can also mask the action, only feeding the pose. But if you think about it, what is this whole thing? If I don't know what the next pose is, but I know what is the next action, based on the token, the cross attention from the encoder, right? I have the current information, current state, current history. I know what action I'm going to take. What you're trying to predict is the next pose. So this is what we call forward kinodynamics.
Yep.
Forward dynamics. Similarly, if you do this, what if you have everything? I'm telling you where you want to reach. That's your pose. Then you are trying to predict what is the action. That is inverse kinodynamics here, right? So those are the two things we do in training. We mask 50% of the chance we mask the pose, 50% of the chance we mask the action. So we can enable two tasks. And there's one more, which is, we call it NP, navigation policy. What if we mask all of them? So this is not done during training. This is only zero shot when we deploy. When we deploy, we can also mask both the action and the pose. You don't know anything. Based on our current state, current token, current context vector, what should you do? What eventually it learns is trying to do, navigation policy is a fancier name for behavior cloning. It's trying to clone the navigation demonstration from the expert demonstration. So this is what we call navigation policy here. Right? That is where the multitask comes into place. And remember, we only need one causal transformer to do that. The difference in tasks is only specified by which input token are you masking. So compared to previous approaches, we actually have a work, which is the prior work of VERTIFORMER is called VERTICODER, only the encoder part, which will be presented at ECRA next week, in Atlanta, is you can learn a encoder which gives you the context embedding. Then you can slap on multiple downstream tasks. For example, you can learn one FKD head, and that FKD head will always give you the next pose based on actions. You can also slap on another IKD head. That's a entirely different MLP. Different head. You can also learn IKD. So feeding the pose you want to reach, it will give you the action as well. Right? You can also slap on another behavior cloning / navigation policy head. It will learn navigation policy. But those are not real multitask, because you need multiple heads to do the different tasks. But here, this is a real multitask, because you only have one transformer model. So the multitask will be enabled, will be specified by which input token you are masking. It will just give you different tasks. So this is the second so the two most important one. And there's also the third one, which is we actually train the transformer. If we go up here, we actually train it in a non-autoregressive manner. So instead of predicting the next pose or next action and feed that into it again, predict the next one and feed that in again to predict the next one. That is autoregressive. So the problem for us is if you do that, the error will accumulate a lot. And for our problem, for this vertically challenging terrain problem, error accumulates very quickly, right? If you are off by a little bit, if you are off by like 1 centimeter, you may be on the rock or you may be not on the rock. And then the next one will be very, very different, right? That's why we do it in a non-autoregressive manner. We directly predict the next 3 pose, action, and terrain patches together. So we actually show from our experiments, we can achieve much better accuracy if we do it non-autoregressively. Of course, you can still do it autoregressively by feeding the first 3 and then do it again, the next 3 and next 3. You can certainly do that as well. But what we find out is, having the 3 is actually more accurate than doing this autoregressively one by one here. So that's the 3 things: unified representation, so that the encoder, the transformer does not need to worry about intra-modality relationships, only focusing on the temporal relationship, unified representation. Missing modality infilling can enable this multitask reasoning, multitask transform model, and also being non-autoregressive can reduce our drift. So it will be able to very precisely do forward, inverse skew dynamics, and also navigation policy. We can also even do terrain patch reconstruction. It can also try to predict what is next upcoming terrain patch, because that is basically one modality here, which we call I here. Right. So that's how the overview of the whole VERTIFORMER work. I guess I can probably still play this video to the end to give an idea so how it actually looks like. So physical experiment, we show this. How do we compare the model using FKD? As you can see, the terrain is actually very, very challenging, right? Because it's not just driving through, because all those rocks are elevation maps we built. So the blue is ground truth from odometry, right? And then the green is the model prediction. We actually use our non-autoregressive model progressively by predicting 3 and 3 and 3. So as you can see, the green is relatively closer to the blue in most of the cases, but this is actually a very difficult task because you don't precisely know how it will diverge from the ground truth, right? So we have some experiments. We put this in FKD. So if it's FKD, we also need a planner to go with FKD. We use the MPPI planner. It is pretty good in trying to avoid all these rocky terrains and can drive through. Of course, it's not a perfect model. We also show some failure cases. This is the IKD. So we have a global planner. Say the global planner say, hey, go there first. That's your current sub goal. And then we feed into our inverse skew dynamics and drive it. So this is actually a failure case to show you how the VERTIFORMER IKD trial can also fail, right? Because we don't want to claim we solved everything. So there's also failure cases we want to include here. As you can see, it is coming up to this failure case here. So it's actually failed to avoid this patch of rock, I think, right here. Because of this hole here, it gets stuck. Right? It won't be able to jump out.
Right.
Yes.
Yeah.
So that is basically, we also have failure cases. So in general, I would say, it's usually much better to do a forward dynamics, especially in our case. IKD is always a little bit difficult.
Yeah. Okay. I was curious. So why are you predicting the maps at test time, like the forward predictions for the
I guess we don't need to. That's just an auxiliary task.
So it was useful like regularization for training then.
Exactly.
Okay,
so
makes
it's
sense.
Basically because of our unified representation, all these things are mapped to the same representation space. So it's just come for free.
Okay, that makes sense. Yeah.
And the other thing is, one thing we actually figured out is can actually try to predict the upcoming terrain. It's kind of like image infilling, kind of like in painting kind of thing, right? If you see half of a rock, even though the next half of the rock is out of your field of view, you will be able to predict. If I see this rock, it's very likely the other half is this way, right? So it gives you a little bit more, perception range. If you say, if you want to think why prediction the patch is useful, that is somewhat usable.
Yeah, and the MPPI planner isn't using that or anything though, because I guess presumably, okay, makes sense. Presumably, it's already redundant with other information that it's predicting, or
exactly
makes sense.
If you go, so that's a lot of detail here, but just to briefly mention that we actually figure out, so sometimes trying to predict the terrain is not very precise. It may also even hurt the performance because it's a very difficult task. Because how would you know what is upcoming? Other than if I see half a rock, I will predict the next half a rock. But most of the cases, you cannot do that. You just don't know what is upcoming.
If the information just isn't there. Yeah, that makes sense. Yeah. Right. Okay. Cool. Why is that same reason for it? Sorry. Why the filling with vulnerable tokens? That's like kind of that's a novel idea to me. Why do you have to fill? Is that also tied into that's also because of the unified space, right?
Exactly. It's because of the unified space. So by doing unified state representation and missing modality infilling, these two things combined can give us this multitask perspective of the whole transformer.
Yeah, sure. So when you say predicting the 3 poles, right? Are they like temporally like evenly spaced? Like, are you in effect predicting the next 3 seconds? Is that kind of like what is happening?
Yes, I think it's next 1 second.
Oh, okay.
So like this is much lower frequency. That's actually also one problem we have with this. The transformer model is pretty efficient because it can be trained within 1 hour of data, but still we cannot catch up the frequency, not like 50 hertz. You won't be able to, even though the transformer is small, you still couldn't query it at like 10, 20 hertz. Like I think we are running it at 3 or 4 hertz.
Is it like running on a Jetson Nano or like something more powerful?
It is running on a Jetson
So it all can't even run on board the robot too, let's say.
Yes.
Yeah.
Yeah, so you can run it on the robot, but this is also hard lessons we learned. So our vehicle is actually 1/10. It can carry at most one NVIDIA Jetson Orin NX, not even the Orin AGX. That's too heavy. We have a 6-wheeled vehicle which can carry the AGX, which is great, right? But for the 4-wheelers, it cannot carry more than the NX. So then, if you think about it, we have lots of heavy-duty compute being running on board, not just a transformer. Transformer is actually a very small piece. We also need to run this elevation mapping because we don't assume access to any of the maps. We are building the map on the fly using the point cloud or the depth images from the Azure Connect, right? That's one. We also need to do VIO. Right, so we need to know the odometry so we can build the elevation map so we know where the robot is. So these two are very, very heavy. Plus the transformer, plus if you want to do MPPI, it is impossible for you to fit all the computation on board a NVIDIA Jetson Orin NX. That's not possible. That is why we think to do this kind of research, it's better for you to work on a 1/5 scale vehicle instead of 1/10. Because for this vehicle, for the DOM, this is actually 1/5. What we did, so this work does not need it. What we actually fit on this vehicle is 2 NVIDIA Jetson NXs. One is only for all the perception tasks, and the other is only for all the planning tasks. This is the sweet spot here. So then everything can be on board. So what we are doing right now with VERTIFORMER is here, because we have an indoor test bed with all the rocks. We sometimes cheat it by not running the VIO on board. We have a mocap. We can have very precise motion capture from external to save us some trouble of dealing with the limited computation on board.
Do you think you could do this with just the depth instead of with the elevation map? What would be the difference there? I mean, I know obviously there's a big difference, but like, what do you think? Sorry.
Yeah, I guess so. We build elevation maps from the depths, right?
Right.
So I would say it's more. So that's our inductive bias. That's our paranoia. We know what matters for you is what is underneath you. I don't care about other things, right? So that's why we use this depth image or /point cloud, that's Azure Connect, to build the elevation map. So elevation map is this, right? So this is the elevation map built by the depth images.
Yeah, I was just wondering if, I guess, I was wondering if you could predict the next like couple seconds just from or how well it would perform at predicting it literally just from the depth images on the real sense, not on the real sense, on the Connect. Yeah.
That's a good point. We do have in our very first paper, so I think we copy so let me quickly towards this paper. In our very first paper, we actually did that, which is a behavior cloning policy. So that's the first paper we introduced all the platforms.
Yeah.
So we have a behavior cloning policy we trained using depth images. So two things, which is kind of tricky here. So I haven't described this whole platform a lot. One thing is you haven't noticed what. If you look at this camera here, right, you will notice there's a servo here. So the whole camera is actuated for the pitch angle to go up and down. Because the problem with not having this servo is whenever you are crawling, the camera will be looking at the sky, right? You won't even see the rocks. If you only use the depth image, it is telling you the depth of the sky. You don't even see the rocks. That will be a big challenge when you only use depth image, right? That is why we actually put this servo here. So it's always pointing down based on the IMU of the camera, right? Then it works decently. I would say that's this result is about, right? We have a data set, so that's what the depth camera give you. You see all the rocks, right? But of course, all these information are redundant. You don't care what's the background, right? So, but you can do a behavior cloning. You can regress from this to actions. You can do that.
Okay.
The performance is okay, right? But I guess one is you need to actuate the camera. So right now we don't actuate the camera anymore, because if we build elevation map, then we don't. Because we know whenever we see the rocks, we build it, right? So that's much easier, and also it's more denser information, because we only care about the rocks. Like giving me the rocks, I should be able to reason about the inverse or forward hemodynamics. I don't need to see any of these, right?
Yeah, I guess that explains the question. So then, if I'm understanding right, the problem with the depth on its own is that the depth on its own is actually not just like only a small part of that image is useful, and you really, to get the useful input you want, you need like multiple integrated depth images and just the part that you care about. And that's why the elevation map is useful, because then you can really get this valuable 2D map of the terrain that it's actually driving over, as opposed to just like some kind of junky depth structured like image. Okay, that makes sense. All right.
Yeah, so can I ask, like, so when you were doing the testing, I mean, when like you collected 1 hour of training, and then did you try to I don't know, mess around the rock again, like completely, or like go to another track?
Yes.
So it's
we
robust
don't
to
need to
all
go
of
to
this.
another. We do all these because the thing is, you don't need to go to another track because all these rocks, if you're strong enough, you can pick them up, put them in a different place. We shuffle this whole test bed like very, very often, right? So that's one. And also you drive different paths, and you also want to induce some dangerous behavior. You actually want to roll over the vehicle once or twice. So the inverse or forward kinodynamics knows, okay, if I drive on this patch with this action, it will roll the vehicle in the next state. Right, so we try to make it as diverse as possible, but it's just 1 hour. Eventually, there's a limit of data we can eventually collect.
Do you think it would continue to improve? It would continue to improve though if you did collect like 24 hours of data or 48?
Definitely.
Yeah,
definitely.
Okay.
We can. I definitely think so. And also, we want to encourage. So we currently expanded this rock test bed a little bit, right? So we're actually moving our lab to Arlington next month. Actually, not next month, June the 3rd. So we are expanding this to a much larger one. What we want to do is rocks, grass, wood, foam, and we also want to add deformable terrain. Sand, mud, all these things that can change its shape. And then, increasing the diversity definitely can help you with better performance. But eventually, it's all about, even if you have 24 hours data, with better algorithms, with better, like, for example, unified representation, you can even push the limit of the performance of the mobility even better.
Can you use the current version of VERTIFORMER to collect the data for the next one? Get that flywheel turning, all that?
Of course, yeah, we can never try that. Yes, yeah. Yeah. It has been a very fun project to work on with all these rocks.
Yeah.
When we are moving the lab, the university is asking us, like, hey, what are you guys moving? I was telling them, okay, 3,000 pounds of rocks.
Yeah. I'm trying to build a castle here, guys. Yeah, I mean, I'm curious, like, did you guys try, like basically, like, humans just try to do this very difficult task? Would you say, like, do you have any gut feel, like, that, I mean, like, there's an RC crowd that do this kind of thing, or like, sometimes there's this game called Mud Runner. I don't know whether you heard of this game. Okay. Basically, it's like this kind of, like, very difficult terrain. Obviously, it's just a game, it's a simulation. Yeah, I wonder if you have any gut feel, like where is it, like, VERTIFORMER versus like what a human would be able to do. I mean, humans, let's say have a third eye view, so maybe not fair, but like also there's a lot of occlusion and all that. So what's your sense?
So I don't know if you see those. I don't know about the game you mentioned, but I know, like, those hobbyists, those Jeep hobbyists. They drive Jeeps over very, very crazy terrain, right? What they have is they actually have an external observer trying to go in front of the wheels, look at the rocks there, and trying to direct the driver to drive, right? That is actually a very interesting thing we want to work on eventually. Because what if you have a secondary robot, which can give you a third-person viewpoint? Maybe that's a drone. You can fly a drone over to scout terrain, to map the terrain first, and then go to places where you want more precise elevation mapping. Then you have more precise, more accurate, navigation on top of that. That will be a very interesting to work on, right? For now, when we collect the data, humans are actually very, very good at driving over this, right? Of course, you can argue when we collect data, we don't just constrain only the first-person view camera image for the human. The human can have third-person view, but they are very good at assessing all these terrains. Observed, because we have a lot of students helping us collecting all these data, right? So 1 hour data is what we collect, is what we clean up. We do have more than 1 hour of data. We have like maybe 10-20 hours of data, but not very clean. But those students help us when they collect the data. They are very good at trying to, they're not sure if this rock is gonna be possible or not. They can always drive on it, attempt it. It's not working very well, backtrack, and trying to accelerate, try to see if you can overcome that barrier or not. So this is still not possible with our planner, right? But that is actually a very valid thing to do. When you're not sure about your kinodynamics response, try to explore that, try to attempt. If you can go through that, great. If not, backtrack and try a different route. So that is something we also want to work on in the future, like kind of like a recovery behavior and also a different strategy. So it's the same rock. If I drive this way, it may not be possible to pass over. But what if I drive in a different strategy? What if I gather some momentum, try to accelerate at the beginning so I can go through that barrier? That's something we want to study in the future as well.
Yeah, I suppose it's if in the real life when you have a human driver driving like a big Jeep, like in this kind of like crazy terrain, that's what the human will have to do. Like he can't be like in an RC car like looking over, right? He can't have alternate views. He probably have to do what you just suggest, like try a little bit, like because literally you don't know what's underground, right? You kind of feel the
Yes.
vibration a little bit. Okay, this is too dangerous, so let me backtrack, that sort of stuff.
Exactly.
Yeah,
What
sorry,
kind
Chris?
of data gets thrown out? So that was saying. Yeah.
So there are bad data where like the odometry is lost, VIO is lost.
Okay.
Those are just not very good data. So eventually, we didn't filter the quality of the driving. If
Okay, that was what I was wondering. Yeah.
So sometimes the elevation mapping have a very big hole there, just because it's messed a whole patch of rocks. Those data are thrown out because that will contaminate the training data. Right?
Makes sense.
Yeah, I guess I also want to maybe quickly talk about this whole thing, which is brand new along this direction, which is called the VertiBench. This is actually an RSS paper this year we did on the same problem here. So eventually, one question people ask is, how do you know your planner is better? How do you know you have better mobility? So mobility is actually very difficult for you to benchmark, unlike perception tasks, right? For perception tasks, we can collect data, right? So like a data set, a kitty data set, whatever data set you have, and compare against the ground truth. That's much easier for you to benchmark. For mobility, it's extremely difficult because you have to roll out your system, you roll out your policy, you roll out your planner. It will give you a different state. Then you don't have data for that. And then you keep rolling out, you will try to evaluate whether the mobility is good or bad. So this is a brand new work we just did, which will be presented next month in RSS in Los Angeles, right? So called the VertiBench. We based on a pretty precise, a multi-body physics engine called Chrono. And we want to benchmark the mobility of these vehicles. So that's why we call everything for us is Verti, right? Verti wheelers, VertiBench, VertiFormer. So this is called VertiBench. It's a benchmark. So we include different geometry, different elevations. We also include different semantics. That's something we haven't done much in the physical world, but we do have that in simulation. Rigid terrain, formal terrain, and we also add different kind of obstacles, through obstacle, rocks, boulder, trees. And also very important thing here is the whole benchmark is scalable to different vehicles. We have our 110 scale, which is this one. This is our RC car, so our Verti wheelers. You can also scale it up to like a full 6-wheel truck, right? Also a full-scale tank. And then the whole environment is also scalable. And then you can study the mobility for these in there as well. So also very relevant for this line of work.
Yes, so what we should do? We need to do an Earth rover like all-terrain version, like do it for real. And pit the human versus like a bunch of these AIs.
Yes. Right? Yeah.
Yeah, but
we're actually building a kind of driving simulator in the lab. After we move to the new lab, we have more space. We actually are building like just basically like Photobot, right? So we have a steering wheel with the whole racing seat. We want to put human in there, let them drive in this high fidelity simulator. So the visuals are not great because that's not the purpose of the whole benchmark. We are not trying to benchmark visual photorealism, right? So what we are trying to benchmark is only mobility, but the mobility here is very, very precise.
Yeah.
And then we can compete against a human, right? If a human can drive from here all the way to the goal, right, so within say 2 minutes, can an AI drive the same thing, avoiding getting stuck between those stands, without rolling over, without getting stuck between a boulder, these kind of things, right?
That would be really interesting to see.
Yeah.
Like how the AI versus human.
Yes.
Yeah, I mean, I guess just taking just between these two papers, what strikes me is, I mean, obviously we've been doing this episode for quite a while now with Chris. I think in robotics, I mean, I'm a casual observer. I'm not a researcher, but just observing. There's a lot of hype, maybe justified, right? Scaling laws, like throwing huge data, huge compute. But there are a bunch of things you are doing here that is just like, why, like this episode is quite refreshing for me. It's like, okay, you're not throwing a big simulation. You're not like getting a farm of H100s. You're doing everything in the real world and you're willing to break robots.
Yes.
And you're relying on really classical, I guess. I mean, the fact that we have like hundreds of years of knowledge of physical, like laws of physics, right? And you really rely on that, second
plus
order
transformers though. So.
Oh yeah, crossfire. Okay, yeah, that one no joke. But the first one, and just relying like using machine learning when it's like more just as a function estimator, right? Because too hard to do the handwritten thing. Yeah, but the further transformer is also really cool. Like you make very careful like options about like how you design the thing. So yeah, just overall very refreshing. And also I think be it VERTIFORMER or also like the DOM, cast and fly. I think both have a lot of actually, let's say, safety implication. I mean, if these things can be scaled up in the real, like tested in real vehicles, I can imagine like eventually if it works so well, like the auto insurance company will mandate, hey, I give you cheaper insurance if your thing can auto adjust when your car is flying, you know?
Yeah.
Yeah, so
Yeah, that is
really cool.
actually a very relevant work to like another paper we're going to present next week at ECRA. It's called CARSTOR, Competence-Aware High-Speed Off-Road Navigation, which is kind of what you described. You put an AI agent in the back end. If you're driving too aggressively on off-road, if you're going to roll over the vehicle when you drive over like a high-friction terrain, but the AI will take over, say, hey, slow down, or reducing your steering angle so you can smoothly make that turn, right? So that is also, very relevant to what you just described. So a system that can help you to be competence aware. Yeah. I guess one very quick comment. Let me also maybe quickly show you this console. So one thing I want to mention is, of course, there's a lot of hype in robotics, and there's a lot of very cool there's a lot of like simulator, lots of large data, these kind of things. But one idea our lab always wants to think about is, there's always corner cases, and there's always going to be adversarial settings, and there's always going to be extreme cases. And we like to work on those extreme cases. So those are the extreme cases we were talking about. If you drive fast enough, you will roll the vehicle. If you're driving fast enough on low friction terrain, you are sliding all the way. If you drive into a, whatever, like a rocky patch, bumping too much will damage the vehicle. All these are extreme cases that, from our perspective, we always need some either guarantee or we need to know what is happening under the hood. Using these classical models, using, say, MPPI, for example, using a kinodynamics model, so we know what will happen, that can help us to push the boundary of the mobility, because that's the focus of our lab. So you saw two directions here, high speed and also vertically challenging. So you also know I run this barn challenge, right? Benchmark autonomous robot navigation, which will also happen next week in Atlanta, which is, can you navigate robots in extremely, extremely confined space? So you have only 2 centimeters on the left, 2 centimeters on the right. Can you make a sharp turn with that much clearance? Can you be confident enough? So those are the things we are trying to aim for. So of course you can say, if with a lot of data, eventually you may be able to solve it. But what our philosophy here is trying to say, okay, there's always gonna be more limit you can push, right? The more limit you want to push, at some point, data may not scale well enough because you don't have that much data when you're operating at the extreme of the vehicle. And that's why we need to borrow not only data, we also use machine learning a lot, but very small scoped machine learning piece, right? We want to combine it with our physical principles. We want to combine that with our, say, a sampling-based motion planner. We want to combine it with constraint optimization. All these things are trying to push, the last bit to push the robot to the extreme mobility limit here. So that's our kind of like whole hypothesis, our whole conjecture here. We want to maintain guarantee, maintain safety, and we want to push the limit to its extreme.
Yeah, I definitely like the idea or the point that we need to look at the extremes and not like the mean or modal kind of use case for robots, because like the whole point of robots is for them to run autonomously, like 24/7 doing something, right? So I feel like if you're in the case where you only care about the kind of like nominal situation, it's not the right place to be doing. Like, what's the point of a robot then? I guess your robot's going to fail after a couple hours, and then you're back to doing it by hand or whatever, right? Yeah.
And also, it's fun to work at the extreme, right? So you see all those crazy behaviors. That's also very, very cool, very, very rewarding when you see the robots operating at its extreme.
Yeah.
Cool.
Yeah, I want to say, like this is our, I don't know, 10 or 11 episode or maybe more now. We've seen some really, really cool demos, but I don't know, personally, this one takes a kick. Like controlling a damn car to fly and then land safely. Oh gosh, I was like, I rewatched that, that clip quite a few times before this episode. But anyway, this is really cool, man, Xuesu. I'm so glad you come to share. And like I said, it's quite refreshing. With all the learning base, like end-to-end, huge compute scaling, and then you come in and say, okay, remind everyone, classical robotics, we have hundreds of years of Newtonian laws. Let's take advantage of that. Yeah, maybe final question that we kind of ask everyone usually. Is there any paper that you come across, from other labs that you think was really cool and maybe you wanted to just give a shout out to?
You think about this. There's so many cool papers, right? I don't know how to pick, I guess. Let me think. There's one paper from Byron Booth's group we have been reading. I forgot the name, which is trying to say, if you have a local map, you're trying to navigate to a long distance goal. How do you learn over, different frontiers. So you will be able to have a guidance from a sub goal, so you can drive to that without getting stuck in local minimums. So I'm just speaking out loud because that's a paper I read like 2 days ago. Right, so that's something, and also very cool experiment. What they did is they put the experiment on a 12-ton tank, which is, of course, is Byron's Overland, Overland AI company. They work on this DARPA project, which I think is pretty cool. They put it on the tank, they put it on the Boston Dynamics spot, and they're trying to learn, over if I see, or even if my LiDAR won't be able to see, there is a forest right in front of me, 200 meters away, but my RGB camera can see that. I know, even though I don't have the map, I know I should not aim at the forest because I may get stuck there. I should go to the side. That is one paper I think very, very interesting. So I asked all my students to read it as well, so we can do something similar with that as well. Yeah, I guess. Yeah. So that's on top of my head.
Yeah, I think this has been a very fun chat. Thank you again so much for jumping on.
Cheers.
Yeah, so we got 2 papers done in one episode. That's great.
Yeah.
Okay, cool.
Yeah.
Yeah, so we'll see you soon. I'll see you in Atlanta, I guess. Yeah, a couple of days time.
I think it's like 5 days, I guess. Right?
Yeah, cool.
Not even 5 days, 3 days, right? It's almost Thursday.
Yeah,
Right.
this is actually this is
Yeah.
it's coming soon. All right, cool. Well,
All right.
see you real
Good
soon.
night.
Okay, Chris, what have you learned?
Hey, yeah, this was a cool discussion of like how we can do all kinds of really crazy robot control using machine learning and classical robotics and kind of a mixture of physics-based priors and stuff like that. And I thought it's a pretty cool demonstration of how some very crazy robot behaviors, I think. It's nice to see. I think you mentioned a few times that it's like more classical robotics, right? And I think one thing that strikes me is that this is kind of what I feel like classic field robotic stuff is going to look like, where it's not all end to end, but you like build in lots of physics priors and knowledge about the world and so on to get things that are really can do crazy stuff reliably, basically. Yeah. Anyway, what did you think?
Yeah, I mean, I like I mentioned just now, I thought it was quite refreshing. Especially, all the recent ones, either very humanoid or like very learning based, like collect data, like simulation and all that. This guy Xuesu didn't do any of those. Well, I mean, he did have the transformer, I would say, but
He had
still,
a couple.
yeah.
But it's also a good point. Like they tested it in in like relatively like freeform environments that aren't like a tabletop with like things nicely arranged and like all the perfect camera angles and all this kind of stuff that you need for a lot of these learning based papers, I guess, which is not a bad thing. But it's a
I like his spirit of like just willing to very willing to break robots. Because I do think that actually maybe the signal to noise is the highest if you actually just observe all the failure states. In his case, the failure cases are very, very painful, I imagine. Like, breaking robots.
The wheel rolling off. Yeah.
So it's like a lot of work, I imagine, just to fix a robot. Yeah, but that was really cool.
Very cool stuff.
I was just thinking, like, if you give to, let's say, a guy who purely, I only do like learning based, I only do like data driven, like I only know on tour. Like, how would that person like solve something exactly like this?
I mean, I am really curious. Like, if you took 100 hours of data, would it perform as well? And like, instead of 1. And I mean, I think there's a good chance the answer is no. Like, I think that there's a lot to be said for having like good physical priors, and the fact that the data is often hard to work with in these kind of situations, right? Yeah. So.
Yeah. Anyway, yeah.
And
I mean, it's also cool to see another like maybe not pure like manipulation stuff. I think this is the first navigation thing that. Oh no. We have another one that there was the one done by Value, right? But that one is definitely very it's basically a world model with self-driving, right? So So okay. Anyway, well, let's do it soon again. Okay, cool.
Yeah. Bye.